Okay, let's get started. And of course, thanks for coming to today's review. I do not plan to give a very detailed review, but rather, go through the concepts and all the important notations. That is the purpose of today's review. The exam 2 will be on next Tuesday. The standard lecture time from 9:30 to 10:45. There will be 20 multiple choice questions. There are 4 options for each one, and there's only one correct answer. So pretty much everything is the same as the first exam. Now let's do the review. Pretty much, everything starts with annuity, right? So the very basic you need to know is actually Annuity Immediate. So in this case, you have n payments. Well, usually we call this n years, right? But the time unit does not need to be a year. That would be the case in Chapter 4. And in a standard annuity, the payment at each time is the same. So here we assume $1. In order to derive the present value, which we denote as A, okay, angle n denotes there are n payments. Sometimes we write this small I, sometimes we don't. This small I is the interest rate for one period. So here usually is 1 year. So this interest rate should always be consistent with the time unit you use. So in most cases, it would be 1 year. In Chapter 4, it could be anything. It could be 1 month, could be 1 quarter. So basically, we are doing just one thing or two things, right? Discounting and summation, right? So throughout this course, while discounting, sometimes, we do accumulating if you want to know the value at time n plus summation. So that's what we do for all the annuities. You do two things, right? Discounting and sum them up. And for instance, the first dollar will be discounted to time 0 by 1 year. So that's V. The second dollar discounted by 2 years, right? V square. The third will be discounted 3 years, etc. until the last one you discount by n years. I think by now that should be obvious to all of you. Now, by looking at this, now what you are doing is summation, because we have already done the first part, discounting. We have already done it. The next step is to sum them up. This is a standard geometric series. So it's 1 minus the ratio. On top, you have the first term is V, put a bracket, 1 minus the ratio. This is the second. This V is not the first term. It's actually the ratio. And then you count how many terms. V1 to Vn. You have n terms, right? And if you want, V is 1 divided by 1 plus I. So here we keep the second one. So this becomes I divided by 1 plus I. So it's 1 minus V to the nth divided by I. So we have the first formula. Let me put it in a box. This is something, we did for exam 1. And this is a standard annuity. Once you have annuity due, you put double dots, right? So what is annuity due? Right? Annuity due is always 1 plus I times your standard annuity immediate. Right? Then you will know the numerator is the same, but now you divide by D. That is because D equals I divided by 1 plus I. Right? So when you times by 1 plus I, you move it to the denominator. It becomes 1 over 1 plus I. Right? That's why you get D. And then you have continuously payable. Then you divide by delta, right? Force of interest. Okay. Then let's do Chapter 3. That is Chapter 3. The first one is 3.1. We do a standard increasing. Okay. So it's a standard increasing annuity. So let me draw the. Right. So I always do this. right? I also suggest you to follow the same step, but well, of course, in the end, it's your choice, right? It's I don't know what percentage, but I guess there will be some of you, never follow my suggestions. That's possible, right? So as long as you are able to figure it out in your way, that's fine. This is different from the previous one which I just showed, because now the amount goes up, right? This is what we actually call the arithmetic increase, right? The amount is fixed. The amount of increase is fixed, right? It's $1. So 1 to 2 to 3 to 4 all the way to n. So this is arithmetic increase sequence. So because this is increasing, so we use capitalized I. So the notation, we just add I. So IA angle n. Right? So everything else is the same. Do discounting, right? $1 is V, $2 is 2V squared, $3 is V cubic, goes on. The second to the last is Vn minus 1, the last is Vn. Right? So we already started how to solve this type of summation, because my first identity here is discounting, right? Once discounting is done, or once accumulating is done, the next step is obviously summation. Right? Summation it's a mathematical step. Here you just need to, you can times by 1 plus I, or you can times by V. The textbook times by, let me take a look. Textbook times by 1 plus I. Well, we can times by V. They are the same. So let's times by V on both sides. And then you get V squared, 2V cubic. Here would be 3V to the 4th, n minus 1, V to the nth, n times n plus 1. Okay, and then we do subtraction, but move one position to do the subtraction, okay? Then what do you have? 1 minus V times IA. So the first I keep, and the second one would be 2V squared minus V squared. So V squared goes all the way to V to the nth, and then I have one more term, which will become negative, right? So that's just what we do. And right, what is this? This is basically the reason why I always suggest you to write down the sum. Right? If you never do that, you probably even can't recognize this term. But if you have done it enough, what is this? What I just bracketed. It's simply here. Right? It's just the annuity immediate. Right? So what is IA? Well, you divide 1 minus V over. Right? Then you get the standard formula for IA. So 1 minus V, what is 1 minus V? 1 minus V is I divided by 1 plus I, because 1 minus V is actually D, right? Or you can just apply the definition. You divide it over, so you can flip 1 plus I to the top. 1 plus I times annuity immediate becomes annuity due, and 1 plus I will cancel one of the V's, so the term goes down from n minus n plus 1 to n. At the bottom is I. This is the formula we have, right? But of course you can use the first one if you want. Right. So this is for the present value. Once you know present value, the future value or the accumulated value is very, very obvious, right? So that's why I never suggest you to memorize the accumulated value, right? Between present value and the accumulated value, things can be easier, right? You just times by accumulating factor, right? There's no need to study the other side. So that which is the same thing as long as you know how to do summation, you know how to do subtraction. You don't need to know both, right? Knowing one is enough to know the other. The same here, IA and IS. Knowing one is enough to know the other. And we usually deal with present value. But if you are more comfortable with the future value, it's okay. Then we have many examples, but for the examples, it's unlikely that you start with $1, right? You will usually start with a different amount. For instance, well, I can simply make it, what do I want? 200. Let's say the first payment is $200. The next one is $250. The third one is $300. Goes on for 10 years, let's say. First thing is, what is the last payment? So it's a geometric sequence. So it would be 10 minus 1, giving you the distance. So that's 9 years. Well, each year you increase by 50. So 50 times 9 is 450 plus the first one, so it's $650 in the end. We want to know the present value, right? So here, when the payments are not standard. Standard means it's 1, 2, 3 all the way to n. This is not standard. You need to figure out the difference. In this case, difference is 50. So you make the first one 50 times 1. The second one would be 50 times 2. Obviously, 50 times 1 is not enough, right? So that's why whatever left would be constant. Right. What is the last one? If you take out 150, it's just a 500. 500 is 50 times 10. Then it's 1, 2, 3 all the way to 10. Right? You just need to get the difference. Right? Difference would be the factor. So what would be the present value? I have 50 increasing annuity immediate plus I have 150 standard annuity immediate. Right? So you know how to calculate, right? Of course, this is just for the purpose of study, and later on, what's really important is to understand everything behind it. Is not to do the computation, because nowadays we have many software like R, like Excel, like MATLAB. Companies don't really need you to compute this, as long as you know this step is really enough. Because let me use R to show you, okay? Because essentially, nobody really wants you to do this kind of computation later on once you get a job. This is to understand to basically understand the concepts of discounting. Let's say we have payments x equals sequence from I think it's from 200. By would be the distance. How many do I want? Length out. I want 10. I don't even need to calculate. So this is my sequence. I show you what is this. So this is all my payments. Now I need to get my discount. Right. So let's just give an interest rate. Let's say 5%. So let's do discount. So we need to discount for 1 to 10. So this is my discount factor. So this is the first year, this is the second year, goes all the way. You can see it's decreasing, right? So if I want to know the present value, I just need to y times x times y and take the sum. So that's the result. So right, later on, as long as you understand, the software gives the result in a second. So that's why the most important thing is to understand discounting and the summation and different kinds of decomposition. How can you decompose a sequence of payments into some standard annuities? That's important, right? Doing the math, doing the computation, it's really nothing, because we have supercomputing power to do everything for us. That's annuity. That is increasing annuity. So of course, once you know increasing annuity, you know many things. For instance, from IA to IS, right? That's the that would be the accumulating value, and from IA we can easily get IA double dot, right? That is the increasing annuity due, right? So everything behind due and annuity, it's simply 1 plus I times the corresponding IA. right? That's it. And then you'll get the result, right? Once you know I double dot A, I can get I as I. So those are really trivial. As long as you know the standard, the rest, times by a factor, discount by a factor, I don't think that's going to be an issue. Then we also have infinity. So infinity is just to take n to infinity. So you are trying to calculate the limit, right? The limit. Did I give you the result down here? So let's. So here is the result, right? So you need to take n to infinity. By taking n to infinity, this term is gone. This power term is gone, and this becomes becomes a perpetuity due, right? It will be 1 over I. So in the end, we will get it's an annuity due, so it's actually 1 over D, not 1 over I divided by I. So what we have is plug in the value for D. D is 1 divided by 1 plus I. So you get 1 plus I to the top, I square. So this is the increasing annuity perpetuity. This is perpetuity one. Well, what you do is to take n to infinity, right? The same. Is 1 plus I times it. So it will be 1 plus I squared divided by I squared. And it's actually 1 over D squared, right? Okay, so that's increasing annuity. Then we are going to discuss decreasing. Right? It's the opposite side. So the first payment is actually the biggest, it's $N. The second one is N-1. The second to the last is $2. The final payment is $1. Okay? So one very hopeful identity is by packaging an increasing one with a decreasing one. Then you get a standard annuity immediate. But the payment will be N plus 1. So from here, you easily get the result, right? So this, your financial calculator can get you the result. This we just derived. So that's why I mentioned a few times that IA, if you really want to memorize a formula, IA would be the only one, right? If you know IA, you know this from your calculator. DA can be calculated easily by doing one subtraction, right? So of course, we can also do the standard thing, meaning I can always write down the summation formula, right? And once I write this down, I know the next step, right? I can either times this by 1 plus I or by V, and then I do subtraction, right? Again, miss one position and do the subtraction, and then you get the result. Okay, I leave that to you. Once we get DA, we get something similar, right? So we can do from DA to DS. We can do from DA to DA double dot, etc. Right? So and then you have DS double dot, and you also have the perpetuity version if you want to consider. Then we move on to a completely different one. So far, increasing, decreasing are on the arithmetic sense. Now we do compound. Compound is geometric sense, meaning draw the graph. So what is the standard? I think we put $1. In the second year, it goes up to 1 plus E. In the third year, it goes to 1 plus E squared. So that is a geometric increase, right? So finally, what would be the amount? 1 plus E to the power of N minus 1, right? Okay, we want to solve this. And obviously, discount everything, right? There are N payments. Just discount. Right? Essentially, there's no difficult, right? And when you solve a question, even you don't know how to do the sum, you do have the calculator, right? So let's say I ask you for 10 years. You just use your calculator to do discounting 10 times, add them together. You can actually do it in one step, right? You can practice, even you don't know anything about summation, right? As long as you know discounting, right? You can always get it done, right? Sometimes it may take longer if you use this naive method, right? So let's say E is 2%. I should be greater than E, let's say 4%. You can literally use your calculator to compute this summation without going through any formula at all, right? I at least trust you to be able to write down this summation, right? There's no difficulty, right? I mean, I can say that. And well, you may say, oh, I can't memorize the formula. I don't know how to do a sum for geometric sequence. At least you should know how to hit numbers in your calculator, right? So what is V? V is 1 over 1.04. And for financial calculator, you can store this number. It's simply STO. Then you put a position. Let's say you store it for the first position. And anytime when you want to use it, you just recall it, right? It won't take more than a minute to finish 10 calculations. So at least there's no excuse for not being able to solve the problem for a relatively short amount of years, right? So if I ask you 100 years, okay, I wouldn't ask you to do the summation because doing this 100 times takes maybe 10 minutes or 20 minutes, and it's very easy to get something wrong, right? But if it's just the 10 years, 5 years, seriously, there's no need to use any formula. Just use calculator to do the computation, right? If let's say here's the 5 years, right? It's this plus 1.02 divided by 1.04 squared for 5 years, right? There's no need to go through any formula at all. But of course, for the purpose of study, we of course we want to know the we obviously want to know how everything is computed, right? And the thing of doing this is here your power is 1. Well, you are trying to match it with V, and then you can put them together, right? So I create 1, and then I have 1 plus E times V, 1 plus E squared, V squared. See here, both of them are in square. For the next term, both of them are in cubic. So I now match them, right? Once I match them, I can use V to replace, use U to replace 1 plus E times V. And this is U squared goes all the way to U to the nth. This looks very like Annuity Immediate, right? But with different discounting factor. So now I need to make this U my new discounting factor. So which means I will let U to be 1 divided by 1 plus J. J would be my new interest rate, imaginary interest rate, right? So J would be 1 divided by U minus 1. And what is U? U is 1 plus E times V. So when I divide by it, it becomes 1 plus I divided by 1 plus E minus 1. So this is I minus E divided by 1 plus E. So with this new interest rate, right, here is at J, okay? At J, not I. So I just need to change the interest rate. Then everything else goes back to the standard annuity. So that's everything you need to know about compound interest rate. By the way, personally, I don't do this because this is just a geometric sequence. Right? I really don't need anyone to tell me what would be this. I don't need annuity. Right? This is just a geometric sequence. When you look at this, right, I directly do the sum. 1 minus the common ratio. What is the common ratio? 1 plus E times V is the common ratio, right? Use the second one divided by the first one. Use the third one divided by the second one. They all share the same ratio. That is the common ratio. The first one is V. 1 minus the common ratio raised to the power of n, because here I have n terms. Right? So this is the formula. Right? This is the end result of my compound annuity. Right? I can do computation from here. I don't need to go through any annuity immediate. The reason I derive this is because you do have the financial calculator, right? Your financial calculator can get you this in one step. That helps you, right? But at much advanced level, you really don't need any formula. The only formula you need is to know how to do the geometric sequence, period. Okay. That's 3.5. What else? We have a quite difficult one. It's continuously payable. That is something many people have trouble with. It's the reason it's because it is continuously payable. So it's rather difficult to imagine how payments are made, right? Because in real life, there's never such a thing as continuously payable, right? So when you deposit the money into an account, the value does not change every second, right? Of course, when you invest in the stock, you can kind of see this. So let's say here is time t. So for the payment, we need to assume a rate. This is the continuous case. So this rate is only effective for a very, very small period of time. Okay. So in mathematics, we call this infinitesimal. So it's the limit case of delta t. Right. Usually we say delta t is some difference. Right. Between two time points, we know the time difference. When this time difference goes to 0, it's infinitesimal. So that's why I write dt. So the amount between this amount of time is your rate times the distance. Right? This is the same concept as if you want to know how far you have traveled in the last 10 minutes, it will be the speed times 10 minutes. Right? Speed times minutes. So here it's the rate times time difference. Okay. So this is the amount. Amount is not enough. We need to do discounting, right? So by discounting, we do continuous version. So it will be exponential from a to t. Your delta s would be the force of interest, because I want to know the discounting factor from the starting time small a to the current time small t. Here I use s for the argument of delta because I'm trying to integrate it, right? So now this is the present value of my payment from small t to t plus delta t, right? And I want to do it from a to b. So in order to do that, we just integrate. Integrate is the limit of summation. So this is the formula. So let's put it in a slightly nicer form. So this is how you calculate the present value, right? So this is the present value. Okay, obviously it's at time a. If I want to know the accumulated value, everything is similar except I don't do discounting. I will need to do accumulating, right? I need to accumulate from t to b. So what I do is from t to b. You see, in the world of continuously payable, when you do discounting, it's exponential of a negative integral. When you do accumulating, it's exponential of positive, right? Because positive will give you something bigger than 1, negative will give you something less than 1. Less than 1, you do discounting. Bigger than 1, you do accumulating, right? So that's the AV formula. That is essentially everything you need to know about the continuously payable. And then we study a few special case. This is a special case. Right. So right now, you know the payment rate is given. So in 3.7, what we study is low 3.8. Your low t is equal to time t. So in this case, you can actually get a nice formula to work with. So first is notation. There are two bars, one on top of I, because this is continuously increasing, right? your payment function is continuously increasing, right? It starts from 0, 0.1, 0.2 all the way high. It's actually more dense than 0.1, 0.2. It's continuously increasing, right? Of course, it is continuously increasing, right? And the second bar on top of A means it is continuously payable, right? Continuously increasing, continuously payable. That's why you have 2 bars. So from 0 to n, low t is t. Your force of interest is now a constant. So delta S is just a delta. So that becomes negative delta t dt. So this is a calculus exercise, right? Where you need to apply integration by parts, right? So let me just show it quickly. I bring in the exponential, so I will need to divide by the constant part, and then it would be negative 1 over delta t times e to negative delta t from 0 to n, then plus, so switch the position. So here I do it again, so I need to divide by another negative 1 over delta. Right, so you get the result. You can keep it as it is. For instance, this one is simply n times e to negative delta n. When you plug in 0, it's 0 plus 1. If you want, you can keep in this form. But if you are trying to simplify, what you can do is, okay. So what is this? E to negative delta is B, right? So it's a 1 year discount. So, right, and for this, take out 1 minus Vn divided by delta. So within the square bracket is actually the continuously payable annuity, right? And then you get the result. So this will be continuously payable. So it's A bar angle n minus n Vn divided by delta. Right. So it takes really similar form, right? So because it is continuously payable, so I on the numerator side I have A bar again, and it is continuously payable, so I always divide it by delta instead of I or D, right? Once I know this, I can also quickly calculate many other things like I bar, S bar, right? I can also calculate, here is n. I can also calculate IA perpetuity. So take n to infinity, right? I can easily get the result. For instance, it's just a 1 over delta minus 0 divided by another delta. It's actually 1 over delta squared, right? You don't talk about perpetuity for accumulating value because it's infinity. Once you know that, the next one is it's actually decreasing. Should be 3.9. So it will be the decreasing annuity, and also okay, they are continuously payable. So now what you do is you assume the payment rate is not t, it's 1, it's n minus t. So it's very obvious to see this result. Not t. So this is rather the continuous version of everything. So note here is n, right? Previously, when we do IADA without bars, those are m plus 1. That's because the reason why it is n is because here is n minus t. Here is t, right? Adding them together is n. So that's why it's n, not n plus 1. So we already know I bar, A bar, right? So it's easy to derive D bar, A bar, right? So once you know that, we can easily calculate the accumulated value. And also, if you want to know the the perpetuity, you need to take n to be infinity, then you get the result. This is pretty much chapter 3. So now let's do chapter 4. Okay, the essential idea of chapter 4 is to change the time unit, right? Before up until to chapter 3, whatever we do is based on 1 year, right? So the time unit, when I draw a timeline, 1 always means 1 year. Now we are trying to generalize this concept. 1 can denote any time, any period of time. It can be 1 year, it can be 1 month, can be 1 quarter, can be 2 months, can be 2 years, can be anything, right? We just need to do a proper conversion, right? So always let I be the annual effective interest rate. Okay, meaning if you put $1 at time 0, in 1 year, you get 1 plus I. Okay, so now we want a different time unit. Let's say we want P times a year. Okay, this means a unit period equals 1 over P number of years, right? Because there are P payments a year, right? Let's say P is 12. Then 12 payments a year, that means 1 over P is 1 month, right? So it's all 1 over 12 number of years, right? So this is the accumulating factor for the unit period. So assume you do have J is the effective interest rate over 1 over P number of years. So this is the definition, right? And we introduce something I upper P, right? This is the annual nominal interest rate. So it's annualized and it's nominal. The only place you actually use it is the piecely. Okay, sometimes we also call this piecely nominal interest rate or convertible P times a year. Okay, it's simply I upper P divided by the frequency P. That gives you the effective interest rate over your new unit period. So let's say, right, J would be the monthly interest rate. So IP would be 12 times the effective monthly. So that gives you the nominal annual interest rate, convertible monthly or 12thly payment, right? So that's the slightly different wording. That is the for the interest rate, and then we also need to discuss the discount rate, right? So for the same timeline, the 1 minus D is actually V, right? So this would be the discount factor for 1 over P amount of time, amount of years. 1 minus the discount would be how you define the discount rate, right? And let's call this dP over P, d upper P over P, right? It's essentially the same concept as J. So with this in mind, you can put it back if you want. You can put it as 1 minus dP divided by P. This is 1 minus the discount rate over 1 over P number of years, right? So in order to go to 1 year, take P, and then you should get 1 minus D. Right? So let me put it in a box, right? And then we can easily connect I with D because this is 1 minus D, which is V, which is 1 divided by 1 plus I. So it's 1 plus I negative. So let's put it back. Let's change it to a different number. Right. So this is how you connect nominal interest rate with nominal discount rate. Right? So you can always go from one to the other. Once you have that figured out, we will need to do various annuities. Now the payments will be at different frequency. I think the first time we started would be 4.4. So now, so let's put 4.4. And the name is Annuity Immediate. Okay, but it's not payable every year. Now it is payable P3, meaning there are P payments a year. So let's draw the timeline. The first payment is 1 over P. The second payment is 1 over P. This is 1 over P. So you still have $1 over 1 year. Is the difference is this $1 is not paid. It's not paid at the end of the year. It's actually paid P times throughout the year at the end of each period. Okay, now one period equals 1 over P number of years. Right? So by this we know I would be 1 plus I to number of 1 over P minus 1. So I would be the effective interest rate for one period. Okay, of course, everything else is the same. In the second year, you continue to receive 1 over P for P times. So you get another $1, right? So you can imagine everything to be the same for the last year. So in the end, you still have $1 for each year. But now this $1 is divided P times into 1 over P for P times. Right? So at the end of the unit period, you will receive 1 over P dollars. Right? But now if you count how many, it would be N times P times. Right? We have a notation for this type of annuity. The difference is here. Okay, you have a superscript, which we read as A upper P. Everything is standard from the previous one, except now you have an upper P. If you want, you can write down all the payments and do discounting if you want. Right? So for instance, this would be VP minus 1. The last one would be V, how many? It's NP divided by P. So that is the summation for all the discounting. But I think I already mentioned many times that I don't like how this is done. I directly from here to factor out this. Okay, and what I do is I use J. This would be 1 plus J to negative 1. This will be 1 plus J to negative 2. Here is 1 plus J to negative NP. Okay, two things I have changed. First, I convert this to a standard annuity. So there is no upper P, right? So 3 changes. Second one, number goes from N to NP because in this notation, N is the number of years. Okay, in this notation, NP would be the number of terms or number of payments in total I receive NP number of payments, each with the same amount. So the amount goes from 1 to 1 over P, and finally interest rate goes from I to J. So personally, I prefer to do this. That is because we are very, very familiar with the standard Annuity Immediate, which has a built-in formula in your calculator, right? But of course, you don't have to take my method. We did derive we did derive the formula, right, in the end, because this is just the 1 minus Vn. That is because Vn equals 1 minus j to negative np. So this is easy to see. Now I want my interest rate, which is j, right? So this is the formula from the previous one, and then we can continue to write P times j. P times j is P times j is the nominal interest rate, right? So it's exactly IP. So it's exactly how IP is defined. So a textbook gives you the second result. It's up to you to decide which one works the best for you. Okay. Once you know the Annuity Immediate, we also have Annuity Due, right? Payable piecely, right? So you know what to do, right? So it's move all the payments one period ahead. That means this is the key. It's 1 plus j, not 1 plus I, because you move one period ahead, not 1 year ahead. Not dot. Right. So once you do this, you will be dividing by dp, and then you have increasing. So let's take a look at the increasing. So now our notation becomes a little slightly different. So in the first year, you still receive 1 over P for each period, which means in total, you will actually receive $1. But for the second year, the payment goes up to 2 over P. So in total, you will receive $2, right? Etc. For the last one, you receive N over P. So in total, you get N dollars. So this has the same idea as a standard increasing annuity, except it's no longer $1 at the end of 1 year, $2 at the end of 2 years. Now each payment, like 1, 2, 3, all the way to N, is divided P times, right? So that's why in the first year, all the payments are 1 over P. In the second, is 2 over P. This is obviously a lot more complicated. So first, let's introduce the notation. It is for the present value, right? It's identical to increasing annuity, except we put upper P now. So this is new. That's because it's payable. It is payable P times a year. So in order to figure this out, you can, there are also a lot of ways you can do. The standard one I do is, of course I need to convert it, right? So, right. So this is for the first year, and this is what you have. So it's P over P, P plus 1, 2P over P. So this is for the second year. So you probably know what would be the last year. right? So this is how you write down the summation. And as mentioned, if the number of years is relatively short, let's say 5 years, let's say quarterly, in total you have 20 payments, right? So the last method, at least that you can do, is to use your calculator to do computations 20 times and add them together. If you're really having trouble, figuring out what formula to use, okay? But from here, what you can do is you can factor out 1 over p, and this becomes 1 over p goes all the way to p over p. The second one I can factor out v e v1, not vp, and then inside I have this. Right, it's the same. You see that? So I can factor out here would be n minus 1. Then I have the same. Right, and actually we have a name for this. Right, this is for this guy. It's actually right, $1 equally payable p times a year, and it is just for 1 year. So once you take this out, well, let's move 1 over p out as well. So what I have is 1 plus 2v plus 3v squared plus all the way to n to this. This is not something new to us, right? This is increasing annuity due, right? Then we have the result for the increasing annuity payable piecely. Once we know IA, we know IS, and obviously we also want to derive the decreasing part. If you are trying to work on that. Let me introduce the last one, and then we will conclude for this review. The last one, the difference is how the payments are changing. So previously in this one, what we know is the increase is for each year, right? So in the first year is 1, in the second year is 2, but within 1 year. Within the first year, all the payments are the same, 1 over p. Within the second year, all the payments are the same, and they are 2 over p. Now we want to do something different. We want the payments to change each by each. So the first one is 1 over p squared. The second one is 2 over p squared goes. So at this point, we receive the p's payment, which would be p over p squared. So you see, this is a lot different from the previous one because even within 1 year, each payment is different from the other, right? So it goes up by 1 over p squared by a fixed amount. So from here to here is second year. So you should know how this increases. Right? So finally, this would be NP divided by p squared. So this is a rather special sequence. We have a name for this. It's I upper P, A upper P. So we have 2 upper P's. The meaning, this means it's increasing P times a year, right? So this means it's payable P times a year. So those the meaning of those upper P's. One means it's piecely payable. The other one is piecely increasing, right? Previously, we don't have this guy because within 1 year, the payment is the same. You can see what is the same between those 2 payments is at the end points, right? So here is 1 over P, here is 2 over P, in the end is N over P. So we are trying to mimic that here. This is 1 over P. this is 2 over P, this is N over P. So they have the same payments at the end of each year, but not in between. So for this, you can try something similar, and pretty much what you will be getting is this. Within the first year, what you have is if you factor out this. If you factor out P squared within the first year, what you have is 1 times V2 1 over P, 2 times 2 over P goes all the way to P times V2 P2P. Right, this is for the first year, and you can easily do something similar for the rest, right? And try to work out a final formula for the last one. So I guess that would be everything I want to say for this review. So let me stop recording. Okay, now if you have questions, feel free to ask. So now it's the standard office hour. So if you have any extra questions, either from textbook or from somewhere else, feel free to ask. And I don't suggest you to do anything extra. Everything is in the textbook. Right? So if you want to practice examples and practice questions from the textbooks are more than enough. If you are able to handle all the examples and practice questions, excluding SOA questions, you will get an A. So that's my last message.
Thank you.